So, this is a lesson on systems of three variables. So first of all, the question should be, what does a linear equation in three variables form geometrically? If you have an equation that looks something like this in very general form, something like that actually forms geometrically a plane. If you had a system of variables that was only x and y, or only y and z, or only two variables, and it was like x plus y equals 7, that forms a line. In three variables, the three-dimensional form of a line is a plane. A system of equations in three variables, first of all, the word system refers to more than one equation. A system is more than one. A system of equations in three variables can have a few different types of solutions. First of all, a system of three variables can have no solution. And we're going to go over what that looks like in a problem as well as graphically in a little bit. But something that has no solution would be considered inconsistent. Okay? You might want to think of the word, the prefix in, as being not or no. So something with no solution is inconsistent. Something which has any solution or a solution is considered consistent. So all it has to do is have a solution to be consistent. Underneath the heading of a solution, we have a couple of different possibilities. If you have a solution, you could have one unique solution. If this happens, if you have one unique solution, it is called independent. One unique solution, independent. So in systems of two variables, if you have a solution where the two lines cross, you would have an ordered pair, an x and a y basically. If you have one unique solution and it's independent in three variables, you're going to have an ordered triple. You're going to have an x, y, and a z value. So instead of just 2, 3, you might have 2, 3, 7, or something like that. You could also have an infinite number of solutions. And if that occurs, those are called dependent. So an infinite number of solutions is dependent. Not to be misconstrued with anything will work, because it won't. But there will be an infinite number of solutions. And again, we'll show this graphically as well as algebraically. All right, so let's get right to some examples here. First example, and I apologize, I'm going to end up probably writing mostly on the right-hand side of the screen because there's something wrong with the left-hand side of my screen. All right, so what we have here is we have a system of three equations with three variables, which means there are three planes someplace out there, and we're trying to figure out, do these three planes have something in common that all three of them would work if I plug values in for x, y, and z. That's the general concept. So how do we take care of this? Well, you have to do a little bit of linear combinations, which is also sometimes called the elimination method. I like to label these equations 1, 2, and 3. And when we go through the process, we're going to use those numbers in order to keep everything straight. So what you want to do is you want to try and find a variable that's easy to combine with another equation, and it's going to make the variable go away when you add or subtract the equation. I like to try and stick with addition if possible. So what I should see is if I look at equations 1 and 2, I've got a negative z there and a positive z there. If I add those two things, it's going to be 0, and that z is going to go away. So my first step is I'm going to take equations 1 and 2, rewrite them, and now by using linear combination, I can simply add straight down. And when I do that, I'm going to get, let's see, 3x and 5x is 8x, 4y and negative 2y is 4 minus 2, so that's going to be plus 2y. And then the negative z and the positive z go away. That's going to be 0. And then I have to remember the right side, which is 8 plus 4 is 12. Well, what you should see is that still leaves us with a combination of two variables and two unknowns. I can't really solve for x or y just yet. So now what I have to do is I have to take any other two equations, not 1 and 2. So I could take the combination of 1 and 3 or 2 and 3, whichever one is easiest for you to deal with. In this case, it looks to me like, I'll do this in green, if I use equation 3, that's got a plus z. Well, again, it makes sense to go with equation 1 because it already has the minus z. You must eliminate the same variable. Okay, if you eliminate the z from the first set of equations, you have to eliminate the z from the second set of equations. You got to keep that consistent. So we're going to go with equations 1 and 3. Rewrite them. Obviously, you want to make sure you're careful to rewrite everything correctly. One of the easiest ways to make mistakes is to copy something wrong. You could have everything else right, but if you copy it wrong, it won't matter. All right, so let's add these two equations together like we did 1 and 2. So we're going to get 3x and 2x is 5x. 4y and negative 2y is plus 2y. And then the z's add up to 0, and that equals 9. So now what we should see is I now have a system of variables with two equations, this one and this one. If I kind of do the same process using those two variables, I should be able to eliminate one more of them. So I'm going to go ahead and rewrite these. I did say I was going to use the right side of the screen. I'm going to try and use the top of the left, and we'll see how well this works. So I'm going to rewrite the blue equation, 8x plus 2y equals 12. And then the green equation, 5x plus 2y equals 9. Now the problem is I can't just add two of these equations together and get rid of one of the two variables. However, what I can do is I can do one of two things. Either I can subtract the bottom equation from the top one, or what I prefer to do is actually take the entire bottom equation and multiply everything by -1. Remember, whatever you do to one side of an equation, you have to do to the other side to keep the balance. So we need to multiply every term by -1. So I'm going to go ahead and rewrite the top equation. If this starts to squiggle on me, I apologize. So that'll be minus 5x minus 2y equals -9. Now I can add these up, and let's see what happens. 8x minus 5x is 3x. The negative 2y and the positive 2y go away. That's what we needed. 12 minus 9 is 3. I now have an equation 3x equals 3. we should be able to easily solve for x dividing both sides by 3. Oh, there's the squiggle. And we get that x equals 1. That's wonderful, but that's only 1/3 of our answer. So we got that x equals 1. Let me see if I can extend this. There we go. What you have to do now is you have to take that 1, and we have to do what's called backfill. You have to go back to either one of the two equations, either the blue or the green equation that we started with, plug x equals 1 and solve for y. It doesn't really make any difference. As long as you do the math correctly, it should work. So I'm going to plug 1 into the 8x plus 2y equals 12. If I do that, plugging 1 in for x, we get 8 times 1. What was it? Plus 2y equals 12. There we go. Let's see. Solving for y, 8 times 1 is 8. Plus 2y equals 12. Subtract 8 from both sides. We should get 2y equals 4. And then dividing both sides by 2, we get that y equals 2. Well, we're getting there. We've got that x equals 1 from there. We've got that y equals 2. Only thing I have left to find is z. What you should notice is that any one of the 3 original equations that we started with, any one of the black equations has both x, y, and z. So if I plug 1 in for x and 2 in for y into any of those equations, we should be able to find z. So let's use, I don't know, let's use the bottom one, just to be different. So I'm going to go back to black here. So that's 2x minus 2y plus z equals 1. What was it? Plus z? Completely forgot what I just said. Plus z equals 1. Yep. So we're going to plug 1 in for x, 2 in for y, and solve for z. Again, just making sure we're following order of operations correctly. Let's see, we're going to get 2 times 1 is 2, minus 2 times 2 is 4, plus z equals 1. 2 minus 4 is negative 2, plus z equals 1. Adding 2 to both sides, we get that z equals 3. So ultimately, our solution is the ordered triple. X is 1, y is 2, z is 3. Okay, that is a point. It's a 3-dimensional point, but it is a point where you have an x, y, and a z value. What does that look like geometrically? Well, here's the answer to that question. Somewhere. Here we go. This is what it looks like geometrically, to have 3 planes intersecting at a single point. As you can see, the green plane kind of looks like it's coming down to the right, the purple plane looks like it's going up to the right, and then the red plane looks like it's kind of flat and goes in between both of them. And what you should see is right here, whoops, it's not drawing on there, but that's okay. Right there at that one single point is our solution. It would look something similar to that. So graphically, that's what it looks like to have one solution, which again is consistent and independent. That is a consistent, independent solution. So let's write that down here. This is consistent, independent. Again, consistent meaning you have a solution, independent meaning one. All right, let's do another example. So we're going to have 5x minus 2y plus z equals 3. 4x minus 4y minus 8z equals 2. And negative x plus y plus 2z equals -3. So again, we're going to pick any two equations that we want to start with that we might be able to get rid of a variable easily. In this case, none of them are exactly the same. The x's have a 5, a 4, and a -1 as their coefficients. The y's have -2, -4, and 1. And the z's have 1, -8, and 2. So it really doesn't make any difference which one we pick. None of them are going to work just by simply adding or subtracting right away. So what we might have to do is we might have to multiply an entire equation by a value and then add it to another equation. So what I see is that if I were to try and eliminate the x's, which I should be able to do pretty easily, if I eliminate the x values, I only have to multiply the third equation by some value and add it to the first equation or add it to the second equation, and we should be able to get rid of stuff pretty fast. So I'm going to use, let's do 1 and 3 first. If I were to use 1 and 3, I would need to multiply the whole bottom equation here by, it looks like 5, in order to make the bottom equation a 5x, a -5x, excuse me, and add it to the first equation, which is +5x, and have those go away. So let's see, I'm going to write the first equation because I'm not doing anything to it. Then I'm going to multiply the entire bottom equation by 5, gives me -5x plus 5y plus 10z equals -15. Now let's add those up and see what we get. 5x minus 5x is 0. That's what we were looking for. -2y and 5y is 3y. Z plus 10z is 11z. And 3 and -15 is -12. So there's one equation with two more variables in it. All right, let's go for, let's do 2 and 3. I think that makes the most sense. If we do 2 and 3, I'm now going to multiply the entire bottom equation by, let's try and, I don't know how to do this the right way. Let's see. We're going to multiply it by 4 instead of 5. So we're going to do 2 and 3. So let's see, the second equation is not changing. So we'll rewrite it. The third equation now multiplying by 4 is -4x plus 4y plus 8z equals -12. And let's see what we get here. So 4x and -4x is 0. -4y and 4y is also 0. That could be good. And wait a minute, -8z and +8z, that's also 0. So I end up with 0 on the left-hand side. That's okay if it happens. But look what you get on the right. I get 2 and -12, which is -10. This gives me 0 equals -10. Hopefully we all know that that's a false statement. What that tells me is that those two planes do not intersect anywhere because I end up with that false statement, 0 equals -10. Because of the fact that those two planes don't intersect, there is no way for all three of them to intersect. So by virtue of getting 0 equals -10, we're done. This thing has no solution. Which, if you remember what we talked about earlier, is going to be inconsistent. No solution. Inconsistent. The prefix in, meaning no or not. Inconsistent. No solution. What does no solution look like? Well, let's check that one out. That was one with one solution. Something with no solution could look like this. All three of those planes are parallel to each other. They never touch. I don't think that's probably what we have in this last case, but that is one possible way they look. Okay, there are other possibilities. of something with no solution. So graphically, again, one way is that all three planes are parallel. They'll never touch, so there could not possibly be a solution. And as you can see in letter C, that's the same idea, all three planes parallel. You also have the concepts of A and B, where in B, two of the planes intersect one plane, but the two planes, the ones on the top and the bottom, the green and the purple, are parallel to themselves. So they don't ever touch all three planes at one place. So there's no intersection there. And then A, it looks like each pair of planes intersects the other one, forming that kind of triangular shape, but they never all touch one another. So the orange intersects the green and the purple at different places. The purple intersects the orange and the green at different places, and the green intersects the purple and the orange all at different places. So you can see that there are several different ways you could have no solution. And that's like the last example that we just did. All right, another example. So we're going to go with x minus 2y plus z equals 3, negative 3x plus 6y minus 3z equals negative 9, and then 4x minus 8y plus 4z equals 12. All right, again, looking at these, the x's have 1, negative 3, and 4. The y's are negative 2, 6, and negative 8. And the z's are 1, negative 3, and 4 for the coefficients. So none of them work out to just add or subtract as it stands right now. So we're going to have to do a little bit of multiplication. I am thinking maybe the easiest one to get rid of here, you could go with either x or z probably. Actually, y wouldn't be so bad either. Let's go with z. It doesn't have to be anyone. You could actually pick any variable here, but let's get rid of z. So I'm going to go with 1 and 2, excuse me. And if I do that, I'm going to need to multiply 1. It looks like to get rid of z by a 3, because that'll give me a 3z and a negative 3z. So let's multiply the entire top one by by 3. So we should get 3x minus 6y plus 3z equals 9. And then the second equation, equation 2, doesn't change. Well, now this is interesting. So it looks like if I add all these up, 3x, negative 6y, and positive 6y, 3z, and negative 3z, again I get a 0 on the left. But look what happens on the right-hand side this time. I get 9 and negative 9. That's also 0. Now, is that a true or false statement? That one should be true. So what that actually tells me is the first and the second are actually the same plane. Okay, those two things are actually identical. So, if that's the case, we still need to do a little bit more checking, because if the third one happens to be parallel, then we're in trouble. Then we won't have a solution. But we have to make sure that that third one might actually intersect the other one. So let's try 1 and 3 and see what we get there. All right, let's see. If I do 1 and 3, I'm still trying to get rid of the z. That was the initial intent. I would have to multiply the top one, it looks like, by a negative 4. So let's see what happens. We're going to get negative 4x on the top one plus 8y minus 4z equals negative 12. The last equation, 4x minus 8y plus 4z equals positive 12. Adding those up, you should be able to see that once again, we're going to get 0 equals 0, which is a true statement. What that tells me, and this is kind of an odd case, is that all three of these are actually the same plane. So because of that, there are an infinite number of solutions. Now that one I do not actually have a graphic for where they're all the same plane, because literally it would just be one plane. But there are other ways which we could have infinite numbers of solutions. So if you get a 0 equals 0 out of one of them, you need to try and check the other ones, because you might find that it looks something like this instead. Here's a situation where all three planes meet, but they meet at one line, not at a point. You should be able to see that the three planes here all intersect, whoops, all intersect right there where it says line of intersection. So that gives you an infinite number of solutions, because a line contains an infinite number of points. So really there is no way for us to determine every single possible point other than to write the equation of whatever that intersecting line is. So this one would be consistent because it does have a solution. So it's consistent, but it's dependent because it has an infinite number of solutions. So there you have an example of all of the major types of solutions that we could get. You could have one solution, which is consistent independent. You could have no solutions, which is just simply inconsistent. Or you could have multiple or infinite number of solutions, because these things actually meet at a line, which is going to be a consistent dependent solution set. And as you can see on your last page, it kind of gives you a set of steps that you can follow in order to try and figure these things out. I think there's 7 steps on there on your worksheet. So there you have it. Those are the possibilities. Those are the vocabulary words that you'll need to know that go with them, and you kind of have a visual as well as the algebra. All right, you guys should have some homework to do with this. Good luck, and get it done.